Hi, I'm Dave from the Department of Physics and Astronomy at Purdue.
My name's Mitch.
And I'm Carly.
Mitch and Carly and I are going to introduce you to some experiments for your students to learn about magnetism. What do we have, Carly?
I have a $20 bill and a can.
We have money in a can, Mitch.
A pickle and 4 grapes.
Pickle and grapes. I've got copper pipe. We have nails. We have compasses. Come join us for 4 amazing experiments that your students will have fun with, exploring magnetism. The first experiment in our sequence, Experiments in Magnetism, is called Tales of Magnets and Nails. It involves interactions between a nail and a magnet, and then 2 magnetized nails. And the goal is to address specific misconceptions that students often have about magnetic materials and magnetized materials and magnetizing materials. You will be provided with some iron nails, some string to suspend the nails, and 2 magnets. The magnets are marked with a dot which represents the North Pole. So you see this is north to south, and they come with a keeper. And the purpose of the keeper is to maintain the magnetic field of the magnets. They will last longer that way. One of the misconceptions that students most often have about a magnetized object like a nail is this: if one end of the object is attracted to the North Pole of the magnet, what happens if you turn the object around? Students will most often say that it will be repelled, when in fact it is not. If the north end of the magnet is attracted to an object like a nail, and we turn the magnet around, what will happen? Again, students will most often say that the action now will be one of repulsion. It'll be repelled. Your students will have multiple opportunities to experiment in various ways with magnets and nails. The first of which will be just to observe, first to predict various kinds of interactions, and then do them and observe them between a nail and a magnet. In the next part, they will actually magnetize the nail and magnetize a second nail. The first nail will be suspended on a string. The second nail will be magnetized, and they will learn that each nail is itself a magnet and behaves as a magnet. Okay, so let's jump back with Mitch and Carly and get going on the first experiment, Tales of Magnets and Nails. Okay, Carly, Mitch, are you ready to get started?
Let's do it.
Okay, so the first experiment is called Tales of Magnets and Nails. And your objective will be to predict the interaction between a magnet and a nail in every possible position that you can think of. So on the paper that you have in front of you, you're going to draw the magnet and the nail in various types of positions, tail to north, tail to south, head to south, middle, top and bottom, every possible configuration you can think of, and then predict the interaction. Your choices will be attract, repel, or nothing, or anything else you might think of. Okay?
Okay.
All right, have fun.
Side like this, so that the end runs alongside of it.
Yeah, okay.
And you could do the other way if you
Right.
wanted to do south and north. Yeah. What's the difference between this one and this one?
On that one, they're both flat, so it would be like this. But on the other one, it's stacked on top like that.
Okay. Could
Yes.
you also go like this?
You could, if it'll stay that way.
I'm going to draw it. For this one, I think they won't do anything.
I think they might repel each other.
Once Carly and Mitch figure out all the possible configurations they can think of between the magnet and the nail, they'll write down their prediction, what they think will happen. Will it attract? Will it repel? Could it do something else?
Wait a second. If the south end and the big end of the nail stick together, then the north end and the big end of the nail should repel, right?
I still think they'll stick together.
Why?
Okay, so now we have our predictions. Let's see what actually happens.
Okay, which one do you want to start with?
Let's just start with this first one here.
Okay. I have the south end touching the large end of the nail.
Well, they look like they stuck together. What if we flip the nail around to the small head of the nail to the south end?
They
Well,
still
also
stick together.
What if we do north end to the small head?
Still sticks together.
What if we flip the nail?
Still sticks together.
So it looks like they stick together no matter which end of the nail is facing the magnet.
Looks like that's the case.
Okay, here's what I would like to have you do. Notice that the magnet has a pole, a north pole and a south pole. Just at the poles. I'd like to have you take the pole of the magnet and push across the nail, kind of like you're smoothing out the wrinkles in a rug. Okay? So swipe about, maybe 10 or 15 times. Don't stop. Come down like a swoop, go across and come up. Come down like a swoop, and just repeat that 10 or 15 times. What that will do is align the atoms in the nail so that the atoms' magnetic fields all point in the same direction. Doing that will cause the nail to be magnetized. Okay? So we're going to have you magnetize your nail, and then we'll experiment with that. Okay?
All right.
All right, go ahead. With both nails magnetized, students will learn that a magnetized nail has a north and south, just like a real magnet, and a magnetized nail, in fact, is a real magnet, just not a very strong one.
Okay, what's next?
So we rub these nails. We're gonna put the magnet over here, and I guess we're gonna see what happens when we get the nails close to each other. Maybe they'll behave differently. Who knows?
Okay.
All right, let's do it. Oh, look at that. They're repelling each other. I wonder if we flip the nail around if they'll attract. They do. Wow.
So cool.
Okay, are we ready for the next experiment?
Yep.
Yeah, let's do it.
Okay, so this experiment is called Don't Cross My Path, and it's all about magnetic fields. So here's your objective. You each have a compass. We have a magnet. Now the magnet has a little dot at one end. And do you know what the dot represents, north or south?
Probably north.
Let's find out. Use your compass.
Looks like north.
Okay, because the compass needle is pointing away from that pole.
Mm-hmm.
The tail is at the magnetic pole. So yes, you're right, it's the north. Okay, so here's what I would like to have you do. Place the magnet right in the middle of the paper, hold it down and draw a trace around it, and draw the pole north and south on the magnet.
Okay.
Once you do that, I want you to each take a compass and put it somewhere on the page. Doesn't matter where. And I'd like to have you draw or mark a point at the tip of the needle. In other words, the pointy end of the compass needle, okay? Mark a point right at the edge of the compass housing, then move the compass so that the tail of the compass adjoins or butts up to that point, okay? Let's have you get started, and then we'll see what it looks like. Are you ready?
Yep.
Okay, go for it.
Okay, Mitch, so this white dot is the north end.
Okay.
So I'm going to mark that, and then we know the other end is the south end.
Okay.
All right. These out of the way. Compass for you, compass for me.
One thing to keep in mind, the compass needle points toward magnetic south. So when a compass is near a magnet, it will point toward the South Pole and away from the North Pole. Now that's a little confusing because if you look at a compass with respect to the Earth's magnetic field, it is pointing to the north. However, for the Earth, the geographic North Pole is the magnetic South Pole.
Now we're
That
putting
can be
the
confusing.
compasses down in order to see if they match with what we feel like we drew. And it looks like they do. And it shows that the field wraps from the north around.
The next experiment in our series is called straw magnets. We are going to go from the macroscopic level, magnetizing a nail, to the microscopic level, looking at what happens to inside a material as it becomes magnetized. We're going to take a section of the straw about 4 fingers wide or 4 fingers long. We're going to hot glue one end, fill it with iron filings, hot glue the other end, and use that as a model for a ferromagnetic material. In this case, the nail that students have magnetized. By going from the macro scale, the nail itself, to the micro scale, the internal structure of the nail, we're going to let the iron filings model the atoms in the ferromagnetic material. So you will see Mitch and Carly do this experiment. You will see them create a straw magnet. They will discover that it does not have a magnetic field. You will observe them magnetizing the straw magnet and discover that it then does have a magnetic field, and you'll see them unmagnetize it. Okay, one final tip before we get started. Just like when magnetizing the nail, when you magnetize the straw magnet, you don't want to stop at any point, because if you do, then the iron filings or our model atoms will be aligned differently at that point than they are in the rest of the material. So you want to come in with a swoop and come out with a follow through and keep it in motion. Okay, so to begin the straw magnet lesson, you'll take a soda straw and cut off a length of about 4 fingers, or about 1/3 of the straw. You'll take a hot glue gun and put a little plug of hot glue at one end. Start at the edge and work your way in. Then you'll take a little plastic pipette, snip off the stem, and snip off half of the bulb to create a little funnel. And you'll use that funnel to fill your straw with iron filings. Add enough glue to create a secure seal. Leave just a little bit of space for them to move around. Then place your straw magnet on a piece of white paper and observe that there is no field. The compass needle will point more or less in a continuous direction, irrespective of the presence of the straw magnet. Then pick up the straw magnet and give it 10 to 15 swipes with either pole of the permanent magnet and lay it down and see what happens. And watch the compass needle as you move it around the magnet. You'll notice that it follows the direction of the magnetic force field, the field lines of the straw magnet. The straw is magnetized. Want to unmagnetize your straw? You can. Pick it up, shake it up, lay it down, and notice it no longer has a field. And here you have an excellent model for magnetizing and demagnetizing an object like a nail. Let's start with the basic premise. Everything is magnetic. Materials are made of atoms. Atoms have electrons. Electrons are charged, electrons spin, and they orbit. And the motion of a charge generates a magnetic field. Permanent magnets and things that can be magnetized, like nails, for example, have a particular arrangement of electrons in their atoms that allows for them to maintain a magnetic field, to be magnetized, to maintain a magnetic orientation among the atoms. Other materials are not quite so lucky. However, since they do have electrons and electrons have magnetic fields, they do interact in an applied magnetic field. So for example, we'll show you a piece of copper tubing, we'll show you an aluminum can, we'll show you a couple of other things. Ultimately, we will get to the grape. Are grapes really magnetic? Well, yes, they are. They react in a magnetic field because of the presence of water. Water responds in a magnetic field. It is repelled slightly, very slightly repelled by a magnetic field, as is copper and aluminum. So materials that can be magnetized and stay magnetized are called ferromagnetic. Nails are made of iron. Iron is ferromagnetic. Nickel, cobalt are also ferromagnetic. Materials like copper and aluminum and materials that contain water are called diamagnetic, meaning they are slightly repelled by a magnetic field. Now that effect is very slight, and to observe it, you have to have a little bit of patience, as you'll see in the following segment. Now a word of caution. We're going to provide you with a neodymium magnet. These slight effects cannot be observed with a normal magnet. It takes a really strong magnet. Neodymium magnets are very powerful. They're very difficult to separate if they stick together, and they can pinch fingers, and it hurts. So for your safety and protection, as well as that of your students, we have cemented the neodymium magnet into a plastic holder. So if it comes in contact with a ferromagnetic material, it will be easier to handle and easier to separate. As you will notice in the video, there's a little bit of a technique to successfully observing these effects. The effect is so slight, if you just approach the object, you're likely not to see much. The technique will be you come close, back up, and try and find the speed at which the object moves and correspond to that. So while we call this "who said grape," other objects will work as well as grapes. For example, a piece of watermelon. We've used pickles. So feel free to explore objects other than the ones we suggest or put into our lesson. One thing that's in the lesson that we did not demonstrate, and that's a piece of graphite, basically pencil lead. And I'll show you that. I have a piece of graphite right here. And as I bring the magnet close to the graphite, you will see that it twists. So the graphite is also, like the other diamagnetic materials, repelled by a magnetic field. Okay, gang, we have some interesting things here, everyday things. We have a pickle, we have some grapes. Would you think grapes would be magnetic?
I don't think so.
Well, we're gonna find out. We have some money. Is money magnetic?
I don't know. Could be.
It could be. Well, we're gonna find out. Here's a piece of copper, and maybe we'll have a few other goodies. Okay, then let's get okay,
sorry.
Pay attention. This experiment is called "Who Said Grape?" Our first example of a diamagnetic material is a piece of copper tubing. Paper money is also magnetic. It is ferromagnetic. It's attracted to a magnet. And similar to the copper tube, an aluminum can is also diamagnetic and is weakly repelled by a magnet. And then we get to the grapes. As you can see, the grapes are diamagnetic. They are repelled, they're pushed away by the magnet, repelled by the magnetic field. If you are receiving materials for the "Who Said Grape" demo or experiment, you will receive a neodymium magnet, some coffee stirring sticks, some string. If you want to try any of the things that we demonstrated, for example, a piece of copper tubing. This is 1/2-inch copper tubing, about 1.5 inches long. I showed you some graphite, and we've also tried coins. United States nickels, quarters, dimes are not magnetic. They don't respond in a magnetic field. They're not ferromagnetic. On the other hand, Canadian nickels and Canadian quarters are nickel. They have nickel content, and they do respond to a magnetic field. They are ferromagnetic. So for a variety, if you'd like to try some Canadian coins, that could be fun too. And it might also be interesting for your students if you try the grape to also try maybe watermelon, cantaloupe, pickle, and they will all respond similarly, and you can have your students decide what is the common element among those things that maybe would cause them to respond to a magnetic field.